Yeah, let's move on our next speaker, Dr. Paul Sánchez.
So thanks to everyone for being here. The work I'm going to present today is something we have been doing at the University of Colorado for the last few months, and it has to do with seismic waves in the asteroid environment. So these are the pictures of some of the asteroids that we have had as mission targets: Itokawa, Bennu, Ryugu, and well, in some years really, Dimorphos, the satellite of the Didymos system. And some of the things that they have in common is that they are small, they are granular in nature, and the missions require them to be in contact with the surface of the asteroid. And these contacts then should generate a seismic wave. However, little is known about the transmission in extremely low pressure environments. At least that is what I have found out. So what do we know? I'm going to be maybe fairly simplistic in this. We know that there are going to be P waves, the pressure waves, and S waves, the shear waves. And the speed of these waves depends on some of the material parameters: the shear modulus, the bulk modulus, and the density of the material. Something else that we know is that, if that is the expression for the shear modulus, this has a dependence on the square root of the overburden pressure, which means that the wave speed is going to have a p to the 1/4 dependency. Has this been observed experimentally? Well, the answer is yes. These are some old, let's say, it's from the 1990s. There's experimental results for tower sand and steel balls. And the lines you can see there, they have these 1 to the p to the 1/4 slope. And of course, for steel balls at about 35 kilopascals, we have a different slope, which is p to the 1/6. And this has not been completely explained just yet. Regardless of that, when the pressure goes to 0, the velocity of the wave should go to 0 too. And we wanted to know whether or not that's true, because if that's so, the velocity of the wave in an asteroid should be maybe just some few tens of meters per second. So we can go two routes. This is an asteroid in all its complexity and all its glory. And if we do it in simulation, we can simulate the whole thing. However, we have a problem. First thing, these are very low resolution. We cannot really have in simulation as many particles as we have in a real asteroid. And the second thing is that we are going to have a pressure gradient. It will go from 0 to something in the center. And this is not what we want to do. The other route we can choose is we are going to just sample the parameter space. We can change the overburden pressure. We can change the cohesive strength between the particles. And we can also change the velocity of an impact. And hopefully we will have an asteroid with somewhere within this parameter space. To do that, we of course need to have a small box with particles, and we will have a much higher resolution for that. So this is what we chose to do. So this is the simulation setup. And at the left, I just have some of the details of the simulation. The important thing is that we're going to apply a certain pressure with a piston on top. The pressure will go from 0.1 pascals to 50,000 pascals. And we are going to start a plane wave by just giving a small kick to the particles on top. And the kick itself is going to change, to have a different velocities for different experiments. So once we do that, this is what we see. And we're going to measure the peak-to-peak time. So this is the time it takes for the peak of the wave to reach to the other side of the container. If we do these simulations with a crystalline lattice, well, this is what we find. This is just the velocity versus pressure. And as you can see, well, there's a bit of a weird behavior that because the velocity doesn't go to 0 as p goes to 0. Actually, there is a plateau. And this plateau, the extent of this plateau depends on the velocity of the impact. But we thought, well, maybe this is just a feature of crystals. Maybe this is just a numerical artifact. And so we wanted to go to the random systems. However, if we go to the random systems, we find something very similar, not exactly the same, but very similar. So what we wanted to do then is just to analyze closely one of of these simulations. So we're going to take this one with an impact of 0.5 meters per second. We're going to focus on that plateau. And if we plot the energy versus height, this is what we find. Basically, this is just the wave moving through the container. However, given that this is a pressure wave, we were wondering, well, what happens with the pressure? Is it doing something similar? And well, yes, it's doing something similar. You can see how the pressure itself is traveling. The thing is, the pressure that is given by the wave is not negligible. Actually, it's a few thousands of pascals. And if we take all the simulations we have done for this specific impact speed, this is what we find. So regardless of the value of the overburden pressure, once we start the wave, the pressure of the container changes to a few thousands of pascals. So really, the pressure that controls the wave speed is the summation of the overburden pressure and the wave pressure itself. So if you have a very tiny pressure, which is negligible in comparison with the pressure given by the wave, for the same impact velocity, you will have the same wave speed. Now, what happens with energy deposition? The dots you can see in there, this is a plot of just energy versus time. The small dots you can see in there, they symbolize the time of arrival of the wave to the other side of the container. And as you can see, well, by the time the wave has reached the end of the container, most of the energy has been dissipated. If we now take all the simulations we have done, what you can see here is that, well, about 90% of the energy is lost within 1 meter. And this is for every impact speed, every pressure, and every strength we tested. If this is so, then maybe we can, I can wave my hand and write some expressions. So energy attenuation then may go as 0.1 to the R. R is just the distance from the source of the energy, meaning that every meter will be able to transmit just 10% of the energy of the impact. And if we also relate this to the 3D geometry of an actual asteroid, well, we need to divide the energy by R squared, and we can then reach the expression on the right. And now, I'm a physicist, so I'm going to make one very outrageous assumption. It is that regardless of the shape, size distribution, packing fraction, our simulations actually do work as a proxy to asteroid regolith. I'm going to also assume that it is true for almost all possible impact speeds. What happens then? What is the implication of this for space missions? Well, for the
2 minutes.
Yes, thank you. For the Hayabusa mission, well, particles immediately surrounding the landing area could have been disrupted, but nothing else. For the Hayabusa 2 mission, the SSI impact did have an effect. Of course, there is a crater, but no particle beyond 5 or 10 meters would have been affected because they just didn't have enough energy to move. For the direct mission, the sample maneuver, which is going to be a 10 centimeters per second impact, is going to cause just little disturbance in the terrain around it. For the DART mission on Dimorphos, well, yes, there's going to be a big crater, but the seismic wave might not reach the other side of the asteroid. And this is a bonus because many times it has been said that possibly small meteorite impacts on asteroids can trigger a Brazilian effect, and that is going to provide a way to segregate particles. And it seems that asteroids are not really going to be shaking that much because of impacts. I think this is the end of my talk. With that, I will just leave you with my conclusions. If you have any questions, please let me know. I will be happy to answer them. Thank you.
Thank you, Dr. Paul. We have one question in chat. So how well do you model results correspond to experimental data regarding influence distance dependence from confining pressure, impact speed, etc.?
Well, it seems that when I go to 1,000 pascals, 50,000 pascals, it seems to be correct. The thing is, the experiments on Earth can go I have seen experiments down to 10,000, but nothing below that. The reason is that you have gravity on Earth, and everything that is related to this goes up to gigapascals of pressure. So that actually does follow the theory. I haven't seen any experiment that goes down to this kind of pressure, 0.1 pascals.